Hello, welcome everyone. In this lecture, we are going to discuss the basic definitions and basic concepts of illumination and laws of illuminations. Okay, so what is light? Light is a part of radiant energy from a hot body which produces visual sensation on human eye. Okay, so light is the cause and illumination is the effect. Okay, so light is a form of radiant and electromagnetic energy. When you heat a body to very high temperatures, that is, whenever you heat a body above its room temperature, it starts emitting electromagnetic radiations. So these electromagnetic radiations can be heat waves. Okay, so if you further increase the temperature of the body, then it will emit the light waves also. Light waves are those waves which the human eye can visualize, which can see as in the form of light. So when a body is gradually heated above room temperature, it begins to radiate energy in the surrounding medium in the form of electromagnetic waves of various wavelengths. Okay, what is incandescent body? Incandescent body is the body which emits light when heated to very high temperature. Because when you start heating any body, at some temperatures they will melt or they will change their state. So incandescent bodies are those bodies which are able to absorb that high temperature, which when heated they emit the light waves at very high temperatures. Various forms of incandescent bodies are the sources of light, and the light emitted by such bodies depends upon the temperature of the body. Okay, so for example, if the body temperature is in the range of 500 to 800 degrees centigrade, 500 to 800 degrees centigrade, it is said to be in a red hot state. It is said to be in red hot state. Remember these temperatures. So what is red hot state of a body? If a body is heated to 500 to 800 degrees centigrade, it is said to be in red hot state. In this state, the body emits the electromagnetic waves in the form of heat. Okay, most of the electromagnetic waves radiated by this body, which is at a temperature of 500 to 800 degrees, will be in the form of heat. Okay, so in red hot state, the body emits maximum radiation in the form of heat. Okay, again, if the body temperature is further increased, when it reaches the range of 2500 to 3000 degrees centigrade, then it is said to be in white hot state. It is said to be in white hot state. In this white hot state, the electromagnetic radiations emitted by the body fall in the visual range or visual spectrum. All the wavelengths of the electromagnetic radiations emitted by this body at this temperature, this fall in the visual spectrum wavelength range. So what we can observe, as the temperature of the incandescent body increases, the wavelength of electromagnetic radiations will decrease. Okay, so for example, when you heat a body, an incandescent body, so when you continuously heat it, what will happen? The temperature of the body increases. So at 500 to 800 degrees centigrade, so it emits electromagnetic radiation in the form of heat. Okay, so and at temperatures, when you further increase the temperature of the body, so in the range of 2500 to 3000 degrees centigrade, what will happen? It will emit radiation both in the form of heat and light. In the form of heat and light. Okay. So light is defined as the radiant energy. It is the some amount of radiant energy from the hot body which can produce the visual sensation upon the human eye. Okay. So all the radiations are not light. Only those radiations which can cause the visual sensation on human eye are called light. Okay. The range of wavelengths of the light are very narrow, that we will see in the next slide. The electromagnetic radiations with wavelengths in the range of 100 nanometers to 1 millimeter is referred as optical range of radiation. Important objective point. So, the electromagnetic radiations whose wavelength is from 100 nanometer to 1 millimeter is referred as optical range of radiation. Optical range of radiation. Okay. Most of the power from the radiation source is radiated in the optical range of the wavelength. So, most of the energy or power from the incandescent body, incandescent radiation source, or you can also call this as incandescent body. Incandescent body is radiated in the optical range of wavelength. Okay. So, what is radiant flux? It is also known as radiant power. Is the radiant energy emitted, reflected, transmitted or received per unit second. So, it is the energy of all the electromagnetic radiations emitted by an incandescent body which is in the range of, let us say, 100 nanometer to 1 millimeter. 100 nanometer to 1 millimeter. Okay. So, the SI unit of radiant flux is what? Okay. And also joule per second. So, there is two different forms, radiant flux and light. Radiant flux is the total electromagnetic radiations emitted by the incandescent body is radiant flux. Okay. So, some portion of this radiant flux causes visual sensation on the human eye, that is called light. Okay. So, radiant flux is nothing but radiant power. For example, a 100 watt incandescent lamp would radiate 100 watt of power. 100 watt of power. Understand? So, that is the difference between radiant flux and the light. The only difference is all the electromagnetic radiations, the energy or power of the all electromagnetic radiations emitted by the incandescent body is radiant flux. Some portion of the radiant flux which can cause visual sensation on human eye is light. Okay. Radiant efficiency. Radiant efficiency is defined as the ratio of energy radiated in the form of light which produces visual sensation of human eye to the total energy radiated out of the luminous body. Yes. What is radiant efficiency? Energy radiated in the form of light divided by total energy radiated by the incandescent body. Also, we can write radiant efficiency as radiant efficiency is equals to energy of light by total radiant flux, right? So, it is the energy of the light by energy of total radiant flux. Understand? So, this will also give the radiant efficiency. Radiant efficiency depends on the temperature of the body. Okay. So, because at lower temperatures, the radiant efficiency is very small because most of the electromagnetic waves radiated are in the form of heat. When emitted light becomes white, that is, it includes all the visual wavelengths from extreme red to extreme violet. So, whenever the incandescent body reaches the white hot state, then only it will emit the visual spectrum wavelengths. Okay. further increase in temperature, if you further increase the temperature of the body, then it starts emitting electromagnetic waves of shorter wavelengths than the violet radiations. These are called ultraviolet radiations. So first it will emit electromagnetic radiations in the form of heat, then it will emit the visual range of wavelengths, and then if you further increase the temperature, it will emit the ultraviolet radiations. So the wavelength of the light varies from roughly from 4000 to 7000 angstrom. 1 angstrom is equals to how much? 10 to the power of minus 10 meter. Nanometer is nothing but 10 to the power of minus 9 meter. You should know these values. Okay, they are repeatedly used for describing the wavelengths of the visual spectrum. So what is the wavelength of the visual spectrum or light waves is 4000 to 7000 angstroms. Okay, the color of electromagnetic waves emitted by the body depends upon the temperature and wavelength. Yes, the color depends. In the visual spectrum, the color of the electromagnetic waves radiated or emitted by the body depends upon both temperature and wavelength. The eye discriminates between different wavelengths in this range by the sensation of color. So, in the visual spectrum, different wavelengths will have different colors, okay, which can be recognized by the sensation of the eye. So, the sensation of human eye is maximum at in the middle of the middle of the visual spectrum range at 5550 angstroms. In some books they will also mention 5500 angstroms or 550 nanometers. Understand? Don't get confused. So even in this range also they can mention from 400 to 700 nanometer. Okay, so this is important. Sensation of human eye is maximum at which wavelength? 5550 angstroms or 550 nanometers. So here you can see all the range of wavelengths emitted radiated by the incandescent body. So visual spectrum is very narrow. You can see visual spectrum wavelength range is very, very narrow. So in this visual spectrum range, so at 400 nanometers we are having a violet, indigo, blue, these Vibgyor colors are there. So what is the wavelength of the violet? Violet wavelength is around 400 nanometers and the wavelength of the red light is at 700 nanometer. And what are the light? What is the color of the light at 5550 angstroms? It is somewhere. It is greenish yellow color. So green and yellow colors have highest sensation on human eye. It is this range, greenish yellow. So where you will have highest sensation, this color will have highest sensation on human eye. Okay, so as temperature is increasing, you can see as temperature increases. So this is how the wavelengths will shift. Wavelengths are decreasing. So in a red hot state, most of the radiations emitted are infrared radiations, and again further you increase the temperature, then it will emit red radiations. Then if you further increase the temperature, it will emit the yellow radiations, like that. So if you further increase the temperature of the incandescent body above the white hot state, it will emit the ultraviolet radiations. Okay, as the temperature of the incandescent body increases, the wavelengths of the radiated flux will decreases. Okay, so human eyes are not equally sensitive to all colors. Eyes are most sensitive in the middle range near the wavelength of 555 nanometers or 5550 angstroms. Okay, so this is the sensitivity curve against the wavelength. So human eyes are not sensitive to all colors. So they are least sensitive to which colors? Violet and red. And they are highly sensitive to green and yellow. So eyes are highly sensitive to yellow and green colors. Eyes are least sensitive to red and violet colors. So an illustration is that a 40-watt yellow lamp appears brighter when compared to a 40-watt red lamp. This is because human eyes are highly sensitive to yellow color. Next, some definitions we will see. Plane angle. This we all know. Plane angle is the angle subtended at a point in a plane by two converging lines. It is denoted by theta and is usually measured in degrees or radians. Okay. So plane angle is the angle subtended by a point in a plane by two converging lines. So the basic definition is theta. In radians we call it as the length of arc divided by radius of circle. So if you assume that the point is at the center of the circle, then this is the arc length. This is the length of arc divided by the radius, which will give the angle theta in radians. Understand? Next, the next important definition is solid angle. Solid angle is the angle subtended by a partial surface area at the center of the spheres. It is usually denoted by the symbol omega or this symbol. Both are omega, either this omega or this omega. Understand? So it is the angle subtended by a partial surface area of a sphere at its center. It is usually denoted by the symbol omega. It is measured in steradian. The unit is very important. It is steradian. Okay. It is equal to the ratio of surface area which is subtending the angle at the center of the sphere to the square of radius of the sphere. So in this image you can see that a small portion of this watermelon is taken out. So the surface area of this conical watermelon divided by the radius square of this sphere gives the solid angle subtended by this small portion at the center of the sphere. Understand? So one thing you have to remember is that plane angle is subtended in 2 dimensions and solid angle is subtended in 3 dimensions. You can see the solid angle is denoted by the yellowish and black portion at this cone. Okay. Solid angle is given by the total surface area under consideration. So here this is the surface area made by this small portion divided by radius square of this sphere. Understand? So if you consider the total surface area of the sphere, then the solid angle will become, for total surface area of the sphere is 4 pi r square divided by radius square, it will give you 4 pi steradian. So the largest solid angle subtended at the center of the sphere is 4 pi steradian when you consider the total surface area of the sphere. So that is the definition. So what is radian? Radian is the plane angle subtended by an arc at the center of the circle whose length matches with the radius of the circle. Okay, understand? So if length of arc is equal to radius of circle, then your theta plane angle will become 1 radian. That's what is shown in the first image. If the length of arc matches with the radius of the circle, then this angle is 1 radian. 1 radian. Understand? Similarly, what is 1 steradian? So it is the solid angle subtended at the center of a sphere by an area whose by a small portion whose surface area is equal to r square. Suppose the surface area here, this is the surface area under consideration. If the surface area value is equal to r square and the radius of the sphere is r, then the solid angle omega is given by surface area, which is r square by radius square is r square. This is 1 steradian. Understand? So these are the definition of 1 radian and 1 steradian. So remember, it is in 2-dimensional plane. This is in 3-dimensional plane. Okay. The relation between the plane angle theta and solid angle is given by, very important, you just remember, omega solid angle is equals to 2 pi into 1 minus cos of theta by 2, where theta by 2. So this is the relationship between the plane angle and solid angle, where solid angle omega is given by 2 pi into 1 minus cos of theta by 2, where theta is the plane angle. Omega is solid angle and theta is plane angle. Okay. Just remember this relationship. So now let us come to the terms used in the illumination. The first one is luminous flux. It is the total energy radiated in the form of light waves per second. So the total electromagnetic. So what is luminous flux? It is the total electromagnetic radiations emitted in the form of light per second. Per second is known as luminous flux. It is represented by the symbol phi or F. Phi or F. And the unit of the luminous flux is lumen. Lumen. Okay. So one important point is that at a wavelength of 5550 angstrom, if a luminous body emits 683 lumen, then it is carrying a power of 1 watt. So what is the point? At 5550 angstrom wavelength, at a wavelength of 5550 angstrom, if a body emits 683 lumen of flux, then it is emitting a light of 1 watt power. This is how you have to understand it. Okay, just for objective questions. So luminous flux is the energy radiated in the form of light per second by the luminous body. It is represented by the symbol phi or F. The unit is lumen. So here in the image you can see a lamp is emitting the luminous flux in all directions. Okay. So the amount of luminous flux emitted is measured in lumen. Symbol is Lm. So what is 1 lumen? 1 lumen is the unit of luminous flux. It is defined as the luminous flux emitted per unit solid angle from a point source of 1 candle power. So lumen is the unit of luminous flux. And how do you quantify lumen? Suppose let us consider a sphere of 1 foot radius, or you can take sphere of either 1 foot or 1 meter. 1 foot or 1 meter. Okay. So let us take a sphere of 1 meter radius. At the center of the sphere, I am putting a point source having 1 candle power capacity. Okay, a point source having 1 candle power, or imagine 1 candle is kept. Now let us consider a surface area on the let us consider a area on the surface of the sphere that is made by 1 steradian or 1 unit solid angle. Then the amount of luminous flux emitted on this surface area is called 1 lumen. Again I am telling you, let us consider a sphere of 1 meter radius, and at the center we are having 1 candle which is emitting the luminous flux. Then let us consider a surface area that is subtended by unit solid angle. So it is 1 steradian solid angle, 1 steradian. Then the amount of luminous flux that is falling on this surface area is called 1 lumen. Understand? So lumens are given by, or luminous flux is given by, candle power of the source into solid angle. So if you know the candle power of the source, and if you know the solid angle in which it is subtending those luminous flux, then you can calculate the total flux or total lumens as Cp into candle power into omega. So total flux emitted by a source of 1 candle power is 4 pi lumen. So at the center of the sphere, what is the total flux emitted by this sphere which is having 1 candle power at the center, it is given by, so total solid angle is 4 pi multiplied by how many candle power? 1 candle power. So 4 pi lumens is the total luminous flux emitted by the 1 candle power source at the center of the sphere of radius 1 meter. So candle power is the light radiating capacity of the source. The number of lumens given out by the source per unit solid angle is called candle power. The number of lumens given out by the source per unit solid angle is called its candle power. It is denoted by Cp. Total flux emitted is candle power into solid angle. This is one important relationship which you have to remember. So 1 candle power emits 1 into 4 pi lumens in all directions. Okay. So candle power is the light radiating capacity of the source. The number of lumens given out by the source per unit solid angle is called its candle power. So in all directions, how many lumens are given out? It is given by the candle power multiplied by the solid angle of the area under consideration. So candle power into solid angle gives the total lumens or total luminous flux emitted by the source. Okay. So unit of candle power is lumen, or it is called lumen per steradian or candela. Very important. So unit of candle power is lumen per steradian. Or other unit is candela. Okay. Next term is luminous intensity. Luminous intensity in any given direction is defined as luminous flux emitted by the source per unit solid angle. So the subtle difference between candle power and luminous intensity is that in luminous intensity we are only talking in a particular direction. The amount of luminous flux emitted by the source per unit solid angle is luminous intensity. It is denoted by the symbol I. It is denoted by the symbol I, and it is usually measured in candela or candle power or lumen per steradian, because the unit will be same, candela, candle power and lumen per steradian. Okay, so luminous intensity in a given direction is the luminous flux emitted by the source per unit solid angle in that direction. So here you can observe a bulb in this particular direction. If you consider a portion which is subtending one solid angle, then how much luminous flux is emitted? Let us call it phi. The solid angle is omega. Then luminous intensity I is given by the total luminous flux divided by the solid angle. So many lumen per steradian or candle, or so many candle power, or so many candela. Okay. So what is candela? So if you again consider a radius, a sphere of radius r, which is subtending an area of r square, then if this portion is illuminated by a power of 1 by 683 watt, then the luminous intensity on the surface is 1 candela. So what is this? We are taking a sphere of radius r, having a light source at the center, having a light source, point light source at the center of the sphere. So now we have considered an area, surface area of r square. So if this surface area of r square is illuminated by a power of 1 by 683 watt, then the luminous intensity on the surface is 1 candela. The luminous intensity on the surface is 1 candela. So these definitions would be very strange. Wordings would be very strange. You have to understand the definition or meaning of the definition. Next is illumination. So when the light falls on the surface, it becomes visible. This phenomenon is called illumination. Illumination is defined as a luminous flux falling or received by that surface per unit area. Okay. So what is illumination? Illumination is defined as luminous flux falling or received by the surface per unit area. It is usually denoted by the symbol E, and it is measured in lux or lumen per meter square or meter candle or foot candle. Okay. So whenever a light falls on any surface, then the light surface becomes visible. This process is called illumination. Light is the source. Light is the cause actually, and illumination is the effect. Okay. So the amount of luminous flux that is falling or received by that surface per unit area is called illumination. It is denoted by the symbol E. It is measured in lux or lumen per meter square or meter candle or foot candle. So illumination is given by, basic definition is luminous flux on the surface divided by the area of the surface. So phi divided by E is given by flux falling on the surface divided by area of the surface, or you can directly write it as candle power into omega divided by so many lux. Okay. So here in the other image you can see that a light source emits light waves or luminous flux in all directions. So if in a particular direction we consider the amount of luminous flux emitted by it, then it is called luminous intensity. So this luminous intensity, some portion of this flux will fall on the surface. Some portion of the flux falls on this surface under consideration. then the amount of flux received by this surface divided by the area of the surface will give the illumination of the surface. It is also called illuminance. Okay, what is brightness? So what is brightness or luminance? So the amount of the luminous flux perceived by human eye, because after falling on this surface some of the luminous flux will be reflected. That reflected luminous flux falls on human eye and the human eye is able to perceive the light. So that concept is called luminance or brightness, that we'll discuss. So what is lux or meter candle? So it is a unit of illumination, we know that. So it is defined as the illumination inside a sphere of 1 radius and a source of 1 candle power fitted at the center of the sphere. Again the same concept. At the center of the sphere you keep 1 candle power source, then at the radius of the sphere is 1 meter, then on the surface area of 1 meter square, whatever is the illumination, the total illumination on the surface of 1 meter square is the 1 lux. Here in the image you can see at the center we have kept a 1 candle power source or 1 candela source. 1 candela is nothing but 1 candle power. And we have considered a radius of 1 meter. The radius of sphere is 1 meter. On the surface area we have considered a surface area of 1 meter square. Okay, the total illumination here is nothing but 1 lux or 1 lumen per meter square. Okay. So brightness or luminance of any surface is defined as the amount of light emitting, passing through or reflected from a particular surface from a unit solid angle. It is usually denoted by the symbol L. It indicates how much luminous power falling on the surface can be perceived by human eye. It is very easy to remember. So luminance indicates how much luminous power falling on the surface can be perceived by human eye. So if the luminous intensity of the source is I candela, then the surface area under consideration is I, and the projected area to the human eye is S cos theta. Then brightness is given by luminous intensity divided by A into cos theta. Okay, so where this is the surface under consideration, this is the human eye, so it will make some angle. So let this angle is theta. So then this is normal to the surface normal. Okay, so here is the lamp which is emitting the luminous flux. Some portion of the luminous flux is taken by the surface and some portion is reflected. Okay, so then definitely it makes some angle theta with the normal. So then the brightness perceived by human eye is given by L is equals to luminous intensity of the source divided by area of the surface into cos theta, where theta is the angle subtended by the human eye to the normal of the surface. Okay, so here you can see a light source in a particular direction. The luminous flux emitted per unit solid angle is called luminous intensity, and the amount of luminous flux falling by the surface area, illumination or illuminance, measured in lux, and some portion of this is reflected and perceived by human eye. It is called luminance or brightness. So this is luminous intensity, this is illumination, and this is brightness. Here the unit is candela or candle power, illumination is lux, or what is the other unit? Lumen per meter square. Whereas illumination unit is candela per square meter. Candela per meter square is the illumination. Okay. So when the light is falling on a surface, it causes illumination, and the amount of light that a human eye can perceive from this illumination is called luminance or brightness. Okay, be careful with the units. Relationship between the luminous intensity, illumination, and the brightness. So brightness, if you directly consider a point light source and a surface directly at a radius r, or at a height r, so if the light is incident directly on the surface without any angle, then brightness is given by luminous intensity of the source divided by pi r square. So all these formulas are valid for this case only, where the light source is, this is the light source and this is the surface. Okay, and the distance between them is r, between the source and the surface is r. In this case, the luminance or brightness is given by I by pi r square, where I is the illumination is given by phi by a, that is Cp into omega by a. So the same thing we can write it as I into the total solid angle subtended by a sphere is 4 pi steradian divided by total surface area is 4 pi r square. So it will become I into r square. So illumination will become luminous intensity of the surface divided by r square. Okay, illumination on the surface. And the relationship between the illumination and the brightness or luminance is given by E is equals to I by r square. If I divide and multiply both numerator and denominator with pi, I am going to get I by pi r square into pi, that is pi into L. So E is equals to pi L. Illumination is equals to pi multiplied by the brightness or luminance, and illumination is given by I by r square. Okay, and brightness L is given by I by pi r square. Understand? So these three relationships you have to, and remember these formulas are valid when the light source is directly falling on the surface without subtending any angle, and the distance between the light source and the surface is r. So in this case, what is the formula? Illumination is given by luminous intensity divided by r square, and the second formula is luminance or brightness is given by I by pi r square, or pi in I by pi r square, that is, or E divided by pi. E divided by pi. Understand? Other terms are mean horizontal candle power MHCP. Mean horizontal candle power is defined as the mean of candle power of sources in all directions in horizontal plane. Just remember, mean of candle power of source in all directions in horizontal plane. Mean spherical candle power MSCP is defined as mean of candle power of source in all directions in all planes. So MSCP is given by mean spherical candle power is given by flux emitted in all directions divided by 4 pi steradians. 4 pi steradians. The unit of MSCP or MSCP are lumen per steradian. Lumen per steradian or candela or candle power. So units for all of them is CP. CP means candle power. So mean hemispherical candle power MHSCP is defined as the mean of candle power of source in all directions above or below horizontal plane. So it is the flux emitted in the below the source in the hemisphere, below the source or above the source. Okay, flux emitted in the hemisphere, either it can be above or below the source, divided by 2 pi steradians. Okay. Reduction factor of the source of light is defined as a ratio of mean spherical candle power to mean horizontal candle power. Remember this formula. So reduction factor is given by mean spherical candle power divided by mean horizontal candle power. Okay. Inverse square law. The illumination of a surface is inversely proportional to the square of distance between the source and the surface under consideration, provided that distance between the source and the surface is sufficiently large so that we can treat the source as a point source. Okay, so the illumination on a surface is inversely proportional to the square of the distance between the source and surface. Understand? So here is a point source as shown in the image. The illumination on the surface of area A1 is directly proportional to illumination E on the first surface is inversely proportional to the square of the distance, that is d square. Similarly, illumination on the surface, second surface E2 is directly proportional to 1 by 2d square, and illumination on the third surface is directly proportional to distance 1 by 3d square. Okay. So this is one very important law, that is inverse square law. The illumination of a surface is inversely proportional to the square of distance between the source and the surface. So from these relationships, what we can write? Illumination is directly proportional to the luminous intensity of the source and inversely proportional to the square of the distance. So illumination at surface is equals to I by T1 square. Similarly, E2 will be I by T2, 2d square, like that. Understand? So the other way of telling the inverse square law is that in order to have the same illumination, let us consider this distance is, say, d. At a distance of 2d, in order to have the same illumination, you need an area which is 4 times to this surface area. 4 times to this surface area. Let this area be A. Here the total surface area required to capture the same illumination is 4A. Here it is 9A. Okay. So at 3 times the distance from the lamp, the lux will be 1/9 because the light is spread over 9 times of the area. Okay. At double the distance from the lamp, the lux will be 1/4 because the light is spread over 4 times the area. So in order to have the same illumination at a distance of d, you require a surface area of A. In order to have the same illumination at a distance of 2d, from the source, you need to have a surface area 4 times that of this A. And at a distance of 3d from the source, you need to in order to have the same illumination, you need to have a surface area of 9 times the A. Understand? Lambert's cosine law. According to this law, illumination varies directly as the cosine of the angle between the normal to the surface and the direction of the incident light. Okay. So suppose if the surface area, the surface which is under consideration is not directly below the light source, is not directly below the light source. Suppose this is a light source, and this is the surface. So now here the incident light is directly coinciding with the normal of the surface. Incident light or incident flux is coinciding with normal of surface. So the angle between the incident light and the normal of the surface is 0 degrees. Understand? Suppose in this case you can see the source and the surface, the point under consideration, it is the normal of surface, normal, and this is the incident light. So the angle subtended between the normal and incident light is theta. So according to this Lambert's cosine law, illumination is directly proportional to the cosine of the angle between the normal of the surface and the direction of incident light. So illumination is directly proportional to cos theta. In the previous cases where we discussed, the theta was 0. Now from the previous inverse square law, what is the relationship we are having? E is directly proportional to 1 by d square. Distance between the source and the surface under consideration. So if we club these two laws, we are going to get what? We are going to get E is equals to I luminous intensity divided by d square into cos theta. E is equals to I by d square into cos theta. Luminous intensity on the surface, which is subtending an angle theta with the normal of the surface, is given by I divided by d square into cos theta. Okay. So from this, if we do the mathematical manipulations, how we can treat d we can treat it as, so if we take the right angle triangle, then we are having h by d is equals to cos theta, then h is equals to, then d is equals to h by cos theta is equals to d. This is h by cos theta. So from this we can directly write, if we replace d with this one, we are going to get E is equals to 1 by h square into cos cube theta, that is I divided by. So illumination can also be given by 1 by h square, I by luminous intensity divided by h square into cos cube theta, where again theta is the angle between the normal of the surface to the incident light of the source. Okay. From the above laws of illumination, it is to be noted that inverse square law is applicable for the surfaces if the surface is normal to the line of flux. That means here theta is equals to d0. So inverse square law is only applicable when the theta is equal to 0. That is, the angle between the surface normal and incident light is 0. Lambert's cosine law is applicable for those surfaces if the surface is inclined at an angle theta to the line of the flux. That is, the surface normal and the incident line is having some angle theta between them. So lamp efficiency is defined as the ratio of total luminous flux emitted in lumen by the lamp divided by the total electrical input in watt to the source. So total luminous flux emitted by the lamp divided by total electrical input power to the lamp. The unit is lumen per watt. Understand? Lm divided by W. So reflection factor or coefficient of reflection, the ratio of luminous flux leaving the surface to the luminous flux incident to the surface is known as reflection factor. So reflected light or reflected flux divided by the incident flux, light flux. reflected light flux divided by incident light flux on a surface is known as reflection factor. It is the ratio of luminous flux leaving the surface to the luminous flux incident on the surface is known as reflection factor. It is a dimensionless quantity. Space height ratio. Space height ratio, it is defined as the ratio of horizontal distance between the adjacent lamps to the height of their mounting. Height of the mounting. Suppose if two lamps are like this and this is the surface, then the height of their mounting is h and the distance between the lamps is d. So space height ratio is defined as the ratio of horizontal distance between them divided by the height of their mounting. So usually its value is between 0.8 to 1.8. Just remember the definitions. Utilization factor. It is defined as the total luminance reaching the working plane. This is working plane. To the total lumens given out by the lamp. Total lumens given out by the lamp. Suppose this is a light source lamp which is emitting the luminous flux, and this is the surface under consideration. Then the total luminous flux reaching this plane. Okay. So it is defined as a ratio of total lumens reaching luminous flux reaching working surface or working plane divided by luminous flux emitted by lamp. So this is the utilization factor. Total luminous flux reaching the plane divided by the total luminous flux emitted by the lamp. Maintenance factor. So it is defined as a ratio of illumination under normal working condition to the illumination under everything is clean. So most of the time what happens, our lamps are surrounded by the dust and some waste material because every day we don't clean all our LED lamps or incandescent lamps and other luminaries. So it is the ratio of the illumination given by the lamp under normal working condition divided by the illumination given by the lamp when the lamp surface is clean. Okay. So flux emitted by lamp normally divided by flux emitted by lamp when its surface is clean. So this is called maintenance factor. So its value will be in the range of 0.6 to 0.8. So for better maintenance, what we do, every weekly once we have to clean the surface of all our lamps so that we get better illumination. Depreciation factor. It is reverse of maintenance factor. So depreciation factor is reciprocal of maintenance factor. The ratio of illumination when the things are perfectly clean, that is to the illumination under normal working conditions. So you can take the definition reverse as that of the previous definition, and its value will be usually greater than 1. The highest value of maintenance factor is 1. The lowest value of depreciation factor is 1 when we thoroughly clean it. So waste light factor. Whenever a surface is illuminated by a number of lamps, there is certain amount of wastage due to overlapping of the light. So waste light factor has a value of 1.2 for rectangular surfaces and 1.5 for irregular areas such as monuments or statues. So in order to properly illuminate, what we'll keep a number of luminaries or number of lamps which try to illuminate a surface or any object. Okay. So due to overlapping of the light, some of the light will be wasted. So that is called as waste light factor. It is in the range of 1.2 for plain surfaces, plain rectangular surfaces, and it is 1.5 for irregular bodies like monuments, statues, etc. Okay. Absorption factor. Because of the mist, dust in the atmosphere, like snow, smoke, dust, these medium absorbs some amount of light before it is being transmitted to the surface under consideration. So absorption factor is defined as the ratio of net lumens available on the working plane after absorption to the total luminance emitted by the lamp. So what is absorption factor? Is the ratio of total luminous flux available on the working plane divided by the after absorption to the total lumens emitted by the lamp. So the value varies from 0.5 to 1. So remaining light is being absorbed by the snow, dust or mist that is surrounding the medium between the source of lamp and the surface under consideration. Okay. So let us take few examples to understand the concepts that we have learned. So a 200 volt lamp takes a current of 1.2 ampere, produces a total flux of 2860 lumens. Calculate the mean spherical candle power of the lamp and efficiency of the lamp. So mean spherical candle power is the total flux, total luminous flux emitted by lamp divided by 4 pi steradian that we have seen in the formula. So it is emitting 2860 lumen and 4 pi steradian. So what is the value? This value will become 227.59 lumen per steradian, lumen per steradian, or other unit is candle power, other unit is candle power, or other unit is candela. Units can be anything. So this is the mean spherical candle power. So this is the first question answer. What is the second question? Lamp efficiency. Lamp efficiency is given by luminous flux emitted by lamp, total luminous flux emitted by lamp divided by input electrical power in watt. So what is the total luminous flux emitted by watt? 2860 lumen divided by what is the input power? Input power is computed by voltage into current, 200 into 1.2 watt. So this value will become how much? 11.91 lumen per watt. So this lamp gives 11.91 lumens per 1 watt. Understand? This is the lamp efficiency. So the next question is, a room with an area of 6 into 9 meter square, it should be 6 into 9 meter square, is illuminated by, this is illuminated by 10 80 watt lamps. The luminous efficiency of the lamp is 80 lumens per watt and the coefficient of utilization is 0.65. Find the average illumination. Okay, so a room of area of the room is how much? Area of room is 6 into 9 meter square, so which is 54 meter square is the area of the room, and total wattage of all the lamps put together is how much? 10 into 80 watt, 10 lamps are there, each 80 watt, 800 watt. Understand? Total flux emitted by lamps, total luminous flux emitted by lamps is how much? 800 watt, each watt is emitting 80 lumens. So this is how much? 64,000 lumens is being emitted by all 10 lamps. Total flux reaching working plane. See, what is the definition of utilization factor? What is the definition of utilization factor? Ratio of lumens reaching the working plane to the ratio of the lumens emitted by the lamp. So utilization factor is this one. So total flux reaching the working plane is utilization factor multiplied by total lumens emitted by the source, that is 64,000 lumen. So it is 0.65 into 64,000 is how much? Its value is 41,600 lumen. This many lumens are reaching the working plane. So average illumination, that is E, illumination is given by luminous flux reaching the surface by area of the surface, that is 41600 lumen divided by what is surface area? 54 meters square. So this value will become 770.37 lumens per meter square, or directly we can write lux. So unit of illumination is lux or lumen per meter square. So the average illumination of the surface is 770.37 lux. Next, third question. The luminous intensity of a lamp is how much? 600 candle power or 600 candela. The flux. Find the flux given out. Also find the flux in the hemisphere containing the source of light and 0 above the horizontal. So what is the question is that a lamp is there. A lamp is giving light in the bottom hemisphere. It is illuminating the bottom hemisphere. So he is telling the luminous intensity is given, and what is the solid angle in hemisphere? Solid angle in for hemisphere, that is half of sphere, is how much? 2 pi steradians. 2 pi steradians. 2 pi steradian. Understand? So luminous intensity value is given as 600 Cp, candle power or candela. So the total lumens given out, total lumens given out in hemisphere. So how many lumens were given out in the hemisphere? The formula is phi is equals to I into luminous intensity into solid angle. So which value will become 600 into 2 pi steradian. So this value will become how much? 3769 lumens. So this is the total luminous flux emitted by the source in the hemisphere. By the source. The source emits this many lumens in the hemisphere.